Okay, in this segment, I want to go over some basic information about semilog plots and about curve fitting exponentials and that kind of thing to hopefully head off some confusion that students typically have in this class when they first start working with these types of plots. So I have MATLAB running here, and I've loaded, as you can see in the command window, the measured data that I'm providing for you for Lab 2. And I've just cleared out a couple of the curves and just changed the names a little bit. So what I've got here are basically applied values of the voltage across the diode connected transistor and corresponding measured values of current. So that's what VD and ID are. So this is actually from the IV experiment as opposed to the VI experiment, but I just want to illustrate here. So if I plot VD comma ID, this is a linear plot, and actually I guess I'm going to plot this maybe using a line style since. Alright, so these are the points on my curve. And one of the things you'll notice here is that most of these points, up until maybe about 0.6 volts, so from about 0.325 up to 0.6, you can't tell what is going on here. This is basically just the current equals 0 on this linear scale, and then all of a sudden it kind of shoots up to, in this case, a little bit more than 10 milliamps here. So these are amps, okay, and these are volts, right? So if I wanted to, I could go X label VD volts and Y label ID amps. And that would be a sensible way of making a linear plot, but this linear plot really isn't telling us what's going on, except for maybe up here in this last maybe 150 millivolts or so worth of VD. For all of this range of VD, we can't really see what's going on. And so that's the purpose of a log scale. If we put this current on a log scale, we can see very clearly what's going on down here, but at the cost of compressing this so that this part of the curve here is squished. And so the way that we make a semilog plot is we use a function called semilog, in this case y, for making the y-axis logarithmic. And so we would plot VD ID. And again, let's put our X label and our Y label in here. And you can see very clearly now what's going on between 0.35 and 0.6, right? So you can see very clearly that this is not all stuck at the same value. In point of fact, you can see that this looks like a nice straight line on this semilog scale, which is the hallmark of an exponential relationship. And you can see it's a pretty nice straight line from here 10 to the minus 9 up to maybe a few times 10 to the minus 3. So 3 milliamps or so maybe, and then it starts to curve over a little bit. You get some bending here. But that's not at all apparent on our linear plot. Okay, so here on this axis we do have the values on the tick labels here are actually labeling current. So this is 10 to the minus 6 amps here, 1 microamp. This is 10 to the minus 8 amps, which is 10 nanoamps. And this is 100 microamps. And this is 10 milliamps. So the labels here on the axis are in fact currents, and the units here that we've put in the label are entirely appropriate. You'll also notice that, and this is another hallmark of of a logarithmic scale, the tick marks start out kind of widely spaced down at the beginning of one of these orders of magnitude, and then they get squished together as you go up near the 10. And then they are spread out, and then they squish together, they're spread out, and they squish together. And that's also a hallmark of a logarithmic scale. So this is what I would like to see for a semilog plot. Sometimes people, when they're asked to do a semilog plot, will do something like this. So they will use plot, and they will put in VD, and they will plot the log of ID. I need capital I, capital V. And the curve looks the same. In fact, it is the same form of curve here. And the x-axis is, of course, labeled the same. What's very different here, though, is the y-axis labeling and the tick marks. So the tick marks here are not at all currents. They are the logs of currents. And log, L-O-G, in MATLAB is log to the base e. So these are the natural logs of the current values here. And so I have no idea what minus 10 means in terms of an actual current level. So, you know, at let's say 0.6 or so, the y-axis here reads minus 10. I don't know what that means. So if you give me a graph that looks like this, these are certainly not amps here, and it's not even clear how to interpret what minus 10 is. So this is where this is like e to the current would be e to the minus 10, right? So I can go down here and I can go exp minus 10, and oh, I can see, oh, that looks that's 4.5 times 10 to the 5th, so that's like 45.4 microamps. So this tick mark corresponds to 45.4 microamps. That's not very illuminating. So what's labeled here are basically factors of E down from 0, down from 1. So 0 on this scale, because log of 1 is 0 in any base. 0 on this scale, which is not even shown here, would correspond to 1 amp. And then minus 1 would be 1 over E amps. And then minus 2 would be 1 over E squared amps, and so on. This is a very unhelpful way of labeling your graph. Okay, so the units of this is not current. The units of this would be like E folds of current down from 0, which is, you know, down from 1 amp. So you know, that's something to keep in mind. So I can do a little bit better if I were to do something like plot VD comma log 10 of ID. Right now, log 10 is the common logarithm, or log to the base 10. And so I have a better feeling for what these tick labels mean here. So minus 6 would be 10 to the minus 6 amps. So right here would be 1 microamp of current, roughly. You know, this would be 10 to the minus 5th amps, which is 10 microamps. 10 to the minus 4, 100 microamps. 10 to the minus 3, that's a milliamp. 10 to the minus 9 is a nanoamp. So this is a little bit better in terms of being able to interpret what the actual y values are on this graph, but it's still much better from the standpoint of understandability and clarity to actually just use the semilog function to actually plot the axis labels here, so that what's being labeled is the actual linear quantity that is in view here at each point, even though the distances here are non-uniform on the semilog scale. Okay? So the units on this scale would not be e-folds of current, but this would be decades of current. So one change in the scale marks here corresponds to a factor of 10 change in current, or 1 decade change in current. And so another thing which is kind of perennially an issue with these log plots is the units of the slope of the line. Okay, so when I make my linear plot here, and I do my x label and my y label, if I were to ask what is the slope of this line here, or the slope of the tangent line to this curve, the units would be amps per volt, or Siemens in the MKS system of units, or mhos in more sort of electrical engineering terms. And that's fine. So we could talk about, maybe drawing a tangent line or an approximation to a tangent line here, and the slope of this linear plot of current versus voltage would be amps per volt. However, if I make the Semilog plot, even though I can label the axes with amps and volts, if I look at this straight line, which is kind of a warping of my linear curve through this logarithmic transformation on the y-axis, I'm tempted to say, well, there's a slope here to this line, and I can find a slope to this line, but the units of the slope of this line are actually not amps per volt, even though the vertical axis is properly labeled with amps. The form of this curve as a straight line is actually coming from that logarithmic transformation. And so depending on which logarithm you're thinking about, what you would conclude the slope, or what you would quote the slope of this line as, would be different. So if you're talking about the slope of this straight line, if we were to have made this type of plot, where we're plotting e-folds of current, or factors of e change in current here, versus voltage, the slope of this line on this scale would be so many factors of e per volt. Strictly speaking, some number of factors of e is not really a unit, but it does help to explain kind of what the voltage is. So the actual units would be per volt, or 1 over volts, because this is really a dimensionless number. But this number, a change in 1 unit of this number, means a factor of e. So if you were to find the slope by fitting a straight line, for instance, to the log of the current using natural log, the slope parameter would be a number in the ballpark of about 38 or so, 39, which would be how many factors of e you would go along this line for a change in the x-axis by 1 volt. And so we would quote that as e-folds per volt. Or if you take the reciprocal, you would find it's a roughly 25.6 millivolts per e-fold. Okay? If instead you were to use log 10, or the common logarithm, where here a change in 1 unit is 1 decade, then the slope of this line would be a different number. If you were to fit a straight line to this x versus the log 10 of the current, you would find the slope of this line would be more like maybe 19 or so, and that would correspond to a 19 decades change in current for a 1 volt change along this axis here. Or if you were to take the reciprocal of that, it would be roughly 60 millivolts for each decade change. Okay? So when you make a Semilog plot, using the semilog command, like I would hope you would do, and you label these axes with proper units. If you do a curve fit and you want to quote the slope of this line, the proper units would be per volt, 1 over volts, or maybe e-folds per volt if you use log. But it's not amps per volt. Okay, so that's one thing. So how would you actually do a curve fit? Well, one approach is to use MATLAB's curve fitting toolbox, and you can certainly do that. If I were to do that on these data, there's a function called fit. So if I say f equals fit VD, and you have to transpose it because it's expecting column vectors, ID, and exp1 is the name of the model for a single exponential. You get here, you're fitting a function to the form a times e to the bx, and it's telling you that the a parameter, which is the multiplicative prefactor, is best fit is roughly 3.96 femtoamps, and here b is basically this parameter, the slope of the exponential, which I mentioned was about 38 or so, 38, and this would be e-folds per volt because we're dealing with a base e here. Okay, and so I can access these coefficients with f dot a and f dot b. Okay, so f is basically one of these fit objects, curve fit objects, and these parameters are f dot a and f dot b. So if I wanted to visualize that on my Semilog plot, what I can do is say something like, put another comma in here to make another curve, so VD, and then I would go f dot a times e to the f dot b times VD, and maybe I'll make this a red line. And you can see it's done an okay job. You can see it's kind of going through the curve, or going through the dots right here, but it's kind of slightly overestimating here, and it's slightly underestimating here, and that's because there's a little bit of curvature up here at the high values, and it's made the best compromise that it can. But it's not done a bad job. And I was actually quite impressed when I did this in preparation for making this video, because the last time I did something like this with MATLAB's curve fitting toolbox, it only paid attention to really the top decade where this slight curvature has taken over, and it's done a really good job fitting up here, but then the straight line extrapolation is off by like a factor of 10 or 50 or something like that by the time you get down here to the low end. So it used to do a really lousy job of paying attention to these data points down here. Because it probably weighted the errors on a linear scale. And down here on a linear scale, these are all basically 0. And any deviation from up here would actually, any deviation between the fit and the data up here would be weighted much more than deviation from between the fit and the data down here. So it's actually improved quite a lot since the last time I tried this. But still, the way I typically will do this kind of thing is I will use my line fit function, which I went over before. So if I were to do that, I would say fit. Let me see, first, last, m, b, n equals line fit VD, and I would pass it the log of ID. So we're fitting a straight line to the log of the current. And here I'm using log to the base e, and I would make my epsilon parameter maybe like 5 times 10 to the minus 4. And you can see that the range of values here that it's chosen is between the 18th point and the 86th point, and the slope it returned is 39, not too far off from the 38 that the curve fitting toolbox gave us. And b here, the intercept is minus 33.6. Okay, and this corresponds to the natural log of the multiplicative prefactor, because e to the b would be broken off here, and could be expressed in the linear space as that multiplicative current factor. So if I wanted to add my line, my theoretical fit, here I can put in VD, and then I would go exp of m times VD plus b. And I'll show that one as a black line. And maybe I'll put my X label and Y label. On here. And you can see, especially if I make this a little bit bigger, you can see actually that the fit that I was able to get by ignoring this little bit up here where the curvature starts going is actually quite a bit better over much of this range than MATLAB's curve fitting toolbox, where MATLAB's curve fitting toolbox tried to make the best compromise for all the data points. You actually do much better if you go with the part of the curve which is a nice straight line, because this is a very nice straight line, and so you get a better read on the slope over probably what we got here, 1, 2, 3, 4, 5, 6, like 6.5 decades of current. So that's the way I would recommend doing the curve fitting. Of course, you can use the curve fit toolbox, and if you want to use this red line here, that's fine. I won't complain about that. If you fit a line that fits well up here in this top order of magnitude, and then the extrapolation goes here and is off by 1.5 decades, I wouldn't be so happy with that, and you might lose a couple points out of 5 on a plot with a fit like that. Okay, so if I wanted to make an annotation on here to indicate that the slope of this line here, let me suppose I get rid of this red one here. So I just have that one. I put my X label, let's say, and my Y label. If I wanted to make an annotation on here to indicate the slope of the line was 39.2, I might say something like gtext slope equals 39.2 e-folds per volt. And just put that right on the graph like that. Or if you want, what may be even better would be, since the model for the ideal diode equation has V over this parameter called the thermal voltage U sub T, we would get that related to M as 1 over M, so 1 over M, 25.5 millivolts. I could go gtext UT equals 25.5 millivolts. Something like that. Just for the sake of completeness, if I wanted to, and I wanted to work with the base log to the base 10, what I could do is I could say log 10 here, and then the slope that I get is different, and the intercept I get is different. The intercept is basically 10 to the minus 14.6 amps, and I get the slope is basically 17 decades per volt, and the theoretical curve I could construct with a 10 dot caret. And you can see it's the same nice fit, but the parameterization is different because I've changed the base of my exponential function from the natural base e to base 10. And here the slope of the exponential would be 1 over m, which is about 58.7 millivolts per decade. Okay, so that's just some information on curve fitting and making exponential, making curve fits to exponential curves, and making semilog plots. So thanks for listening. We'll see you next time.